14.2, data capture and digital imaging. What? Alright, let's talk about CDs. Before we get to digital cameras though, let's talk a little bit about film. Film uses a convex lens to focus light onto, or a film camera uses that convex lenses to focus light. The chemicals in the film react to the light depending on the wavelength of the light. The photosensitive chemicals change with that electromagnetic radiation, and then you can take it and you can develop it so that you get your pictures. The optics of a digital camera are exactly the same as the film. There are a series of lenses inside the camera that focus light from outside onto something in the back of the camera. Instead of the film, though, the camera has what's called a CCD, or a charge coupled device. And this CCD converts the image into a digital form, which can be stored on your media storage device, your little SIM card, your whatever it is that you slide into the camera. And here's a picture of one that came out of an actual camera on the left here. And you can see, if you ever have an old camera, you get a new one for Christmas, take your old one apart and you'll actually see the CCD. It's usually black, kind of shiny, and it's made out of silicone. And when light shines on it, it reacts. Within that CCD, there are a whole bunch of tiny squares that we call pixels. Okay? And those pixels are made up of a photodiode. And that photodiode absorbs light, it absorbs electromagnetic radiation, and it acts like a capacitor. And that capacitor is simply something that can store electrical potential on it once it's been placed there. They have a lot of different uses in electronics. But instead of the battery producing the potential difference on the capacitor, like would happen in a circuit, the light that shines on the photodiode actually produces that potential difference. When light shines on the photodiode, it actually, through the photoelectric effect, causes electrons to be ejected from the surface. The electrons actually move from their original position into another place on the surface of that photodiode due to the absorption of the electromagnetic energy, and they create what are called holes. They're basically just these places where the electrons used to be. And when that electron is freed from the silicon atom, it's trapped, and it's trapped by what's called a channel stop, which is just a place where those electrons can go and be held and stored until everything gets reset. It's basically like an insulating barrier that separates all of the photodiodes. And so what this does is it allows the capacitor to store charge. When we're talking about capacitance, our capacitance equation is Q divided by V, or charge divided by potential difference. Okay, charge divided by potential difference. That gives us the capacitance of a system. When the light is focused on the CCD, these electron hole pairs are produced on each of the pixels. And for every photon of light that is absorbed, you get one of these electron hole pairs. And so what that means is the more photons that hit a pixel, the more of these electrons get bumped off. And so that's one of the ways that we establish different levels of light and brightnesses on the picture is by the intensity of the light shining on it. So the more intense the light, the more of these pairs are produced. And so in that way we can determine how much of a given color is going to be on a given pixel. And to help the color, they actually use filters. And so on each of the pixels, you have 3 or 4 separate diodes, and it depends on the camera and the quality and everything. And so looking at this image here, each of these series of 4 colors here, you have 2 greens, a blue, and a red. And so you have, let's see, you have 4 photodiodes here. 2 of them have green filters over them. 1 of them has a red filter, 1 of them has a blue filter. So the blue one only lets blue light through, the red one only lets red light through, the green ones only allow green light through. And so in that fashion, each pixel can create any color that it needs to with that combination of green, blue, and red. And so however much blue light gets through, red light gets through, or green light gets through each of those photodiodes is what determines the color. And then of course you have however many number of pixels, each pixel being made up of those multiple photodiodes. And then it can take those intensities of each of those 3 colors and convert that into a series of ones and zeros, just like we talked about when we talked about converting analog to digital signals. And so you have this now binary code for your picture. And each of those signals gets stored individually as it gets moved into what's called the serial register. And the serial register is the bottom row. It's the final row on the CCD. And let's see what I'm doing here. If we imagine that this is our picture, and so you have an image of, that's not what I wanted to do. But let's imagine that we have a triangle. Okay, and so you have this triangle here, and you can see if you look closely, just being depicted here. Let's get that out of the way. Each of these little dots here is an electron, and so, or is where one of these electron hole pairs is. So here's our object, it's a little triangle. We take a picture of it. You have this series of blocks with light being shown on them. Now our signal gets moved down. It gets shifted down to the next frame. And so you can see we start, here is our original triangle, and then it gets shifted down 1. And the serial register records everything that's on this series of pixels. And then it gets shifted down again. And the serial register records everything that's on this series of pixels. And then it gets shifted down again and down again and down again until the entire set of pixels has been recorded, converted into binary form, and now it's set on your digital storage device. If you think about it like an array of buckets collecting water. So you have this set of buckets collecting water, and it rains a different amount in each bucket, and you're trying to keep track of that. And so once all the rain has been collected, this first set of buckets is going to dump all their water into the serial bucket array, just like our CCDs are going to dump all of their holes into the serial array on the CCD. This array is then going to record how much water is in each one of these buckets. And it's going to record that in its specific location on the CCD where it came from. And after it's done measuring that entire row, then the next set of buckets is going to fill the serial array. It's going to record that, and so on and so forth until all of the measurements have been recorded. But realize that just like with anything, this isn't a perfectly efficient, 100% perfect system. Not all of the photons that are incident on the CCD are actually going to produce these electron hole pairs. Some get scattered by the surface, not all of it gets through our filters, just like you look out a window and you see a partial reflection in the window because not all of the light gets transmitted. So we have this idea of quantum efficiency. And it's how efficient is the CCD at the quantum level. It's simply the percentage of incident photons that actually produce one of these pairs. And right now we're operating at about 70 or 80%, again, depending on the quality of the camera. Now the better ones are up a little over 80%. And the higher the quantum efficiency, hopefully it's obvious, the better the quality of the image, the more accurate the image is actually going to be. And as we mentioned, that the optics of digital cameras are just like the optics of regular cameras. The light comes through, it gets refracted, and we have our image created. And depending on the position of the object relative to the lens, there's going to be some amount of magnification. And our amount of magnification is simply the ratio of the image height to the object height. So HI over HO or LI over LO if we're talking about length, anything like that. And realize that obviously our image has to be smaller than our object. The CCD is often only a centimeter tall, whereas our objects are varying sizes, most of them more than a centimeter. If you're taking a picture of a person, it can't be person size because your CCD is not person size. And so the larger our CCD is, though, the larger our actual image can be, the less our magnification has to be, and the better the quality. At this point, they're ranging from about 6 millimeters to 16 millimeters, and just like with our TV sizes, that measurement is on the diagonal from corner to corner. But again, also, the larger the CCD, the more pixels we can fit on there as well. And then related to that is the resolution, and this is simply how much detail we can pick out. It doesn't have anything to do necessarily with the magnification. You can have something that's very, very big, but also very blurry and very hard to see with very little detail. You can also have something that's very small, but that's very detailed, and you can see all the little pieces of it. So when we're talking about the resolution, we're talking about the number of pixels on the array and specifically how many within a given area. So if you have a CCD that has an array of about 1800 by 1600, that gives us a total resolution of 2.88 megapixels. Right? It's just the area, the length times the height. For the human eye, our resolution is about 11,000 by 11,000, or about 120 megapixels. So once we get to the point where companies are selling cameras or screens that have resolutions over 120 megapixels, well, then there's no point, because your eye can't discern anything above 120 megapixels. So when somebody comes to your door trying to sell you this great camera that has a 150 megapixel resolution, don't buy it. So if we kind of look at this a little bit more closely, here we have an S, and this image here is our actual S. This is what it looks like. If we were to take a picture of that using a CCD array that was 6 by 7, okay, so an array of 42 megapixels, that S would cover 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pixels on that CCD. When that was converted into a digital image, it would look like this blobby disaster over here. Hard to determine that it's actually an S. However, if you were to take that same object and project it over a much larger set of pixels, you can see as we increase the number of pixels, we also increase the quality of the image. So our S here, which is over, as you can see, I'm not going to count them all, but obviously over a much larger number of pixels, you get much more detail in the resolution. You get much more detail in the image because every pixel that has light shining on it is going to show up in the digital image as the entire pixel. You don't get partial pixels, and this is that kind of binary idea. It's either on or it's off. It's not going to be part of the pixel. It's all or nothing. And so that's why it ends up getting blocky. But now, obviously, we have gotten to the point where our pixels are very, very small, and we can have a lot of them over a very small area, and so we can get pretty significant and pretty clear resolution with our images. But the resolution of the camera doesn't necessarily tell us how good it is at separating objects optically. And this has to do with the light shining on it and the lenses that are being used to focus that light. And so in order for objects to actually be resolved, what we find is that in a digital camera they have to be separated by at least 2 pixels between them. If there's less than 2 pixels between 2 objects, then you will not be able to discern them as 2 separate things. And this is affected by the magnification of the camera and the pixel size. So the smaller the pixels are, the easier it would be to separate them by that 2 pixel width. And it also is going to obviously be affected by how much the camera can magnify the object. So if it can't shrink the object down enough, then it's not going to be able to get that, again, that 2 pixel separation between the two. Now originally, CCDs were pretty poor quality, and this was primarily due to the large nature of the photodiodes. And so again, just like with the S's, you weren't able to fit a lot of pixels onto that area, and so pictures were grainy. They didn't come out very clear. But as technology has progressed, and obviously cameras and iPads and things like that are an enormous market with billions of dollars in them, there's a lot of money then being put into improving the quality of the CCDs, both the magnification, the size of the photodiodes, the quantum efficiency. And so, as we mentioned, the quantum efficiency is about 70 or 80%, and that goes up with each passing year. With regular film, it's really only about 2% with chemical-based film. And so you can see that just in that regard, the digital camera is far superior. And we also find that we can make CCDs sensitive to a much wider range of electromagnetic radiation than just conventional film. And you can see that most significantly, take your TV remote and click it towards your camera, and you can actually see the light at the end of your camera remote, which is infrared radiation. You can actually see it lighting up in your camera because the camera is sensitive to that infrared radiation, and it usually is projected as some kind of purplish or violet light. But that's kind of a cool trick to do. Digital photography also obviously gives you instant results, so you don't have to waste a roll of film. You take a picture. If it's good, you keep it. If it's bad, you delete it and you make room for more pictures. You can store them electronically on your computer. You can Photoshop them. All of those wonderful things that we can now do with pictures, and you don't have to store them in massive photo albums. However, if all of our digital technology dies on us, that was a bell. But as I was saying, if all of our technology dies on us, as in the hit show revolution, then you're going to lose all those pictures and we'll be blasted back into a world without technology, fighting for survival with sticks and bows and arrows. Hopefully that doesn't happen anytime soon. I don't expect it to. So, if you have questions about this, ask your teacher. Good luck, and we'll see you next time.